speaker is Tali Pinsky, and the talk, a heterogenic trefoil for the Lorentz equations.
Thank you. Let me share my screen. Hang on. Okay.
We see your screen. Okay.
And maybe I'll use this. So, okay. So I want to thank the organizers for inviting me. I'm going to talk about the Lorentz equations that we heard a lot about today. And my purpose is to convince you that the topological knot type of this heteroclinic connection is important for the dynamics. And so this is partly joint work with Christian Bonatti. Okay. So that's the plan. I'll talk a little bit about the Lorentz equations, about the geometric model, so the classical model and a new geometric model. Then I'll talk about relation to the geodesic flow on the modular surface. And then I'll come back to the actual equations and talk about the T-point there, the primary T-point. Okay. So here are the Lorentz equations. We already saw them, and the classical parameters are 8/3, 10, and rho is equal to 28. On R3, and here are some properties. So the equations have three singular points in the origin and in both of the so-called wing centers of the attractor that we just saw. I'll show it again in a minute. The equation is dissipative, so volume contracts. And the flow is transverse to a large enough sphere. So we also saw this. It's actually a large enough ellipsoid, and but topologically it's a sphere. So for any sphere large enough, that's true. And there is a symmetry. We also talked about that today. And for the classical parameters, we know there's an attractor. So, sorry. So for the classical parameters, we know numerically that there is an attractor. So here's the attractor. And here there's the singularity of the origin that touches the attractor, which makes it only singular hyperbolic or sectionally hyperbolic and not actually hyperbolic. Here there are two other singular points at the wing centers. And I'm going to add in the infinity as another singular point, which is a source. So from the infinity, I take a large enough sphere and everything is going to come in through the sphere. So I say the infinity is a source for the Lorentz equations. Okay, so the geometric model that we already saw in the first talk of this afternoon, here's the classical geometric model. And it's a classical question, one of Smale's questions. Is the dynamics of the ordinary differential equations the same as that of the geometric Lorentz attractor? And as we know, this was answered numerically, so using rigorous numerics by Warwick-Tucker. Okay. So one of the main motivations for this talk is the relation between the Lorentz equations and the modular surface, or the geodesic flow on the modular surface. So the modular surface is the hyperbolic surface. So in this half-plane model of the hyperbolic surface, you take this fundamental domain where you take the gluings that are generated by, you translate by 1 to the right. So this means you're gonna glue, sorry, this edge with this edge over here. And then you're also gonna glue this part of the edge here with this part of the edge here by using the rotation around I. So Z goes to -1/Z. And this gluing is Z goes to Z plus 1. Okay, so this is the group that is generated by these two mappings is this discrete subgroup of isometries of the hyperbolic plane. And if you take the quotient by this subgroup, you get this hyperbolic surface, this shown here. So this is called the modular surface. It has 2 special points and 1 cusp at infinity. And maybe you're familiar with that this modular surface is the space of all lattices in the plane. And there are 2 special lattices. So this special point will correspond to just square lattices, and this 0.3 will correspond to these triangles. Okay, so now, okay, let me say this. On any hyperbolic surface, when you choose a point on the surface and a direction at the point, then there's a unique geodesic going through that point, and you can follow this geodesic and get to a new point and direction. So for any hyperbolic surface, you get a 3-dimensional flow defined on this hyperbolic surface together with the circle of all directions at a point. So it's a 3-dimensional flow, and as the surface is hyperbolic, the flow is Anosov. So this fact is due to Anosov. And so the flow is defined on the unit tangent bundle. The unit tangent bundle is a space of points on the surface together with a direction at any point. Usually this unit tangent bundle is a complicated 3-manifold. We don't know so much about it, but specifically for the modular surface, the unit tangent bundle is embedded in S3, and it is equal exactly to the complement of this knot called the trefoil knot. Okay. So this trefoil knot is this knot here, and everything outside the trefoil, every point outside the trefoil knot corresponds to a point and direction on a surface, and therefore this geodesic flow is defined there. Okay. So this is the geodesic flow, and so here in black is also, this is also a trefoil, just a different projection of the same knot. And here in red, you see a closed geodesic. So a closed orbit of the geodesic flow in the unit tangent bundle, in the 3-dimensional manifold. Is okay, yeah. So we have a different flow, it's volume preserving, it's a very nice flow. And there are periodic orbits, so infinitely many. On the surface, a periodic geodesic will self-intersect, but in the unit tangent bundle, it will not. Okay, so it's a simple closed curve. Okay. So here's a theorem of Etienne-Gys from 2006. And the theorem says that the closed orbit of the geodesic flow on the modular surface are identical to the closed orbits of the Lorentz system, okay? And what actually Gys proves is that there is a template branch surface that you can construct for any Anosov flow. So he constructs the template for the geodesic flow, and he gets this branch template, which is exactly the Lorentz template. So it's exactly the template that you would get from considering the geometric model of Lorentz and crushing it in one direction. Okay. So what does that mean? He proves that every periodic orbit sitting somewhere here, you can isotope so that it sits on this template. Okay, so if you ignore the trefoil, you get exactly the same set of closed knots, so closed simple curves in S3. Okay, now note that here the boundary of the template is just a closed curve. So actually in the Lorentz system, you do not get all of these periodic orbits. You get a subset. So because in the classical parameters, there's a certain leading sequence, the tips of the triangles are not at the edge of the rectangle, then you get only some subset of periodic orbits at the classical parameters. So actually the theorem kind of should read, because it uses Tucker, that in the Lorentz system, in the classical parameters, the set of periodic orbits you get is a subset of the periodic orbits you get for the geodesic flow. Okay, and of course, this uses Tucker. So he actually knows the theorem. He actually knows how to prove analytically the theorem for the geometric model. Okay, so now this part is joint with Christian Bonatti, and we want to start with a classical geometric model, and we want to extend it in a certain way to show this relation with the modular surface that appears in G's theorem. So we take the regular geometric model and we add.
Interrupt. On the boundary of existence of Lorentz attractor, the needing sequence is just we have full horseshoe.
That's
Is
true.
it true that in this case you have exactly a template, exactly everything what happens in geodesic flow? Or?
Yes, but I mean, if we had Tucker for that parameter, so rho is about 24, yeah, then we would have Jesus' theorem. So we have exactly the same set of periodic orbits.
Ah, okay, thank you. Okay. So the obstacle is only needing sequences determined fully. Okay, thank you.
Yes, yes. So Tucker proved his results for the classical parameters, or for a small neighborhood around the classical parameters. So this neighborhood does not get to rho is equal to 24. So there could be, you know, as far as we know, stable orbits there, or orbits that spiral around some of these hyperbolic orbits. So, okay, if that doesn't exist, then you get the same set of orbits. Okay, I want to complete this geometric model to S3. So I'm adding these two fixed points, and I'm making this direction their unstable direction. Okay, I can do that because I mean the geometric model was not defined in this piece, so I just add another piece here. Okay, then I'm kind of performing a Hopf bifurcation. So I'm making these new stable orbits, which means now that the triangles of the return map go until the edge of my rectangle, because I mean I could put the edge there. And now these orbits became stable, okay? So it's like going beyond the Hopf bifurcation in the original Lorentz. Okay, and now I can slowly, so let me show the previous one. I'm gonna pull the tips of the triangles until they enter this domain of attraction of the wing centers. So I slowly pull them until I get to this point, okay? A very, very similar, identical even bifurcation was considered in a paper of Shivnikov and Turayev. But here, the nice thing is that we consider the model completed to S3. So we're not asking when is the birth of the Lorentz attractor, but just how can we connect the geometric model to the geodesic flow. So when the tips enter into the basin of attraction, then I make this separatrix connect to the wing center. Okay, I force it to, and this is stable. And then there's another direction going to infinity. I add infinity in as a source, and I get a flow that is complete on S3, but I can still control. So this is the bifurcation shown only on the cross section. So you just take this tip of the triangle and you pull it here. Okay. We can control the fact that we do not lose our dominated splitting along this one parameter family of flows. So we have a parameter R. For R less than 0, we have a flow that we know what the chain recurrence set is. So it's a union of these two sinks, one source at infinity, and one Lorentz attractor that is the regular attractor together with the origin. And then for R greater than 0, so after we connect the tips of the triangles to the new singular points, then we have a flow that is topologically equivalent to the geodesic flow outside this trefoil, okay, off this trefoil. So let me just say, whenever I have this invariant trefoil here, it's invariant. So I can consider the flow on the trefoil complement. So then I get a flow on the same space as the geodesic flow on the modular surface. And I claim that on that space, the flows are topologically equivalent. And this is not hard to prove. It's just, it follows from this return map that is just, it crosses the rectangle from side to side. So it's very simple. Okay, so now let me quickly go on to the actual equations. Okay, so I'm going to claim I can find this kind of invariant trefoil, so a heteroclinic connection that is a trefoil knot for the original Lorentz equations. And at that parameter value, so at a parameter value where this trefoil exists, I claim that the Lorentz equations are, well, they're not orbit equivalent, but they're related to the geodesic flow or to this extended, the new geometric model. Yeah, okay, so as a corollary, when the trefoil exists, then you can note that every modular knot appears. This is also related to your question, Dima. So when I call it a T-point, but I actually don't care if it is a Bykov T-point in the sense that it is unstable, that these are saddles, the wing centers, or it's a stable kind of T-point where I just have this connection, but it's stable because these are sinks. So in any case, I get the same set of periodic orbits. It's just not an attractor maybe. Okay. So there are two main components. The first one is this theorem of Chen. He proves that, well, he proves that there are infinitely many homoclinic orbits in the Lorentz equations. I only need the first two. There are also other peoples that worked on existence of homoclinic orbits. So it's easier to prove existence of homoclinic orbits because there's a higher dimension. So this is the first one, this homoclinic butterfly that we also saw today. And this is the second homoclinic connection. And okay. Yeah, hang on, let me see. Okay. What I'm going to claim is that because I have a domain that is simply connected, so any loop can be contracted, then between these two curves, the curve of the first homoclinic connection and the curve of the second, I can find a point where I have my trefoil connection. So if you try to continuously move from one of these homoclinic orbits to the next one, you have to pass through this singularity at some point. Okay. So here, this is a point where you pass this other singularity, so you have this invariant trefoil. As I said before, this is an unstable T-point in my language. So here, this is really a saddle, but I can also have a similar thing that is stable. Okay, the second component is you can find a simply connected domain where you have a nice cross-section for the flow. So in this picture here, this is the paraboloid where z dot is equal to 0. So trajectories kind of go up outside of this, they go in through these red domains, and then they go downwards until they go out at some point. And you can take kind of, part of this paraboloid and cut here with some fixed plane. Z is equal to, I don't know, epsilon or something like that. You want this above the origin, of course. And every trajectory will have to pass through this cross-section downwards. So it's not hard to construct. Okay, and now this is, I'll try to end here. This is a bifurcation diagram taken from Shilnikov's paper in 1980. And it reappears in this paper of Shilnikov and Shilnikov with Barrio. And so here, this first curve is the first homoclinic butterfly, and this curve here, L4, is the second homoclinic butterfly. And in between them, we have this curve L2, this one, where you have this switch between, between this picture here, which is where I have my trefoil, to this picture, well, the separatrix will go around the boundary of the attractor, sort of, to this region here, where you have the, where you have the Lorentz attractor. I mean, there will be here another curve where you lose the foliation, and here there's this domain where the Lorentz attractor exists. But anyway, here on the left of this curve L2, I will have an open neighborhood of parameters where I have my stable trefoil heteroclinic connection. And it is easy to prove because you have this cross section where the map is really 2 to 1, that in these parameters, every periodic orbit of the geometric model or of the geodesic flow will be a periodic orbit for Lorentz, okay? But it's not an orbit equivalence. There could be more. In Lorentz, there could be more periodic orbits. So if you make one of these periodic orbits stable, then you can spiral around it and add kind of more types of knots to your periodic orbit set. But these are, I don't know, kind of trivial, or they can be collapsed onto their, Lorentz knot cores. Okay, so let me just say here in this domain, I have the unstable T-point, and also, of course, the classical parameters are somewhere in there. Okay, and the last thing I want to say is that there's also, of course, a next curve, this one, L5, a next homoclinic curve, and then somewhere in between here, you will have a next T-point that has a different knot type. So it's a figure 8 knot. So there was a talk mentioning the figure 8 knot yesterday. I didn't understand so much of that, but there it was the suspension flow on the figure 8 knot complement. Here for Lorentz, we get a new hyperbolic flow on the figure 8 knot complement. Okay, so I'll end here. Thank you.
Thank you for interesting talk. Questions, comments?
So, is it correct that, okay, you probably said this, I mean, you did say this, that when you say trefoil, it could be T-point or maybe not T-point. So it looks like you prove the existence of this second T-point, but the first T-point is not proven. Is it correct?
Right, that's correct.
Okay.
I prove that the separatrix needs to connect to the singular point for some point in parameter space for any path connecting these homoclinic orbits. But I don't know if at that point the wing centers are stable or unstable.
Yes, but between L4 and L5, they are unstable, so it is really T-point. And between L1 and L4 is not clear. Okay, never mind.
Hey, Talia.
Because of the hi.
Good to see you finally. Nice talk. I mean, stay on this picture, please. I requested. I talked to Taka many years ago, and requested that he would try his magic at least at the second point, slightly on the right from that foliation curve, when you lose the foliation. Just don't tell him about losing foliation first. So we can have a pure experiment whether his integer numerics can do that. Right? And also I asked him to do something like this when the foliation curve, you see when it crosses the L2 curve, right? I said, can you verify that? He never responded. So that's why I have doubts. If he can do that, I'll accept gladly, right? But he never responded, he never tried, and it's kind of suspicious to me, honestly.
But for NO maps, he was able to distinguish between.
Dima, that's fine, but I'm not talking about NO map.
I mean, his magic for other systems, he did both. He found,
I mean, very likely you told him something right before.
I mean, okay.
Don't open up the cards first. Let's make it, the purest experiment ever. So I'm more than happy.
I mean, you're right.
If you can do that.
I mean, you should check.
I mean, my point is that, right? It's just I mean, you don't have to defend him. I mean, it's just as simple as that. Just do it.
Okay.
I mean, it's also that if you want to understand something global, then this very local result is not so useful.
Right, exactly.
I also have a question. Conley has a theorem that whenever you have a periodic orbit which is knotted inner free, then you have positive topological entropy. Your results of the same spirit or are related, or it's different, or just.
Yeah, so I get, for these points where I have my trefoil, then I can bound from below the topological entropy. Yes. It's related to your, Thurston-Nielsen theory, because if you go to this ideal 2-to-1 map, you get the geodesic flow, you only tighten things up, right? So you take it's the Thurston-Nielsen canonical form for your diffeomorphism on the cross-section. So you only lower the topological entropy to get to your ideal representative.
Do you mean you use a cross-section or in your proof?
Yes, yes, I use a cross-section.
I also suggest, Dimo, that entirely let's get together and talk about because you said, I mean, you emailed me your text, right, and wants to discuss it, right? So we can get together later on.
Good.
I might go.
Given that classes are over, right? Then
I might go to Israel in a couple of months. We can meet there.
Huh?
Ah, good.
I might go to Israel in a couple of months because we could meet there.
All right.
No, I just continue to your suggestions.
Yes.
Okay. Thanks, Tali, again.